Gravity is the rulebook of the cosmos. But what if the rulebook is wrong? Our own spacecraft, the Pioneer probes, drifted off course in a way that defied every prediction, revealing a tiny, unexplained push from the sun. This is just the beginning. You are about to discover 30 cosmic mysteries that expose the cracks in our understanding of gravity, from galaxies spinning too fast to an unseen force ripping the universe apart. By the end, you will see the universe not as a settled fact, but as a living puzzle with secrets that could completely rewrite physics. We will explore why stars at the edges of galaxies defy gravity's pull, and what strange object might be hiding in our own solar system's frozen depths. Are you ready to question the force you thought you knew? Our first messengers to the giant planets, Pioneer 10 and 11, carried with them the best predictions of our physics. Yet as they journeyed beyond Saturn, a faint, persistent whisper of a force began to tug them back towards the sun. This was the Pioneer Anomaly, a tiny, unaccounted-for acceleration so small it was like a single grain of sand pushing against a massive ship. It was a deviation so minuscule, approximately 8.74 times 10 to the negative 10 meters per second squared, that for years it hid in the data. Scientists led by figures like Slava Turyshev embarked on a monumental detective hunt, sifting through decades of information stored on archaic tapes and forgotten formats. They accounted for every conceivable influence, from the gentle pressure of sunlight to the faint recoil from the spacecraft's own radioactive heat. The most likely answer emerged as anisotropic thermal radiation, the simple idea that heat radiating unevenly from the spacecraft's body could act like a tiny, unintended thruster. Yet for a time, this tiny push opened a profound question. Was it merely a thermal effect, or was it a crack in the foundation of gravity itself? A hint that Einstein's rules behave differently in the deep, cold silence of the outer solar system. The lesson of Pioneer is one of cosmic humility. It reminds us that our most precise maps of reality are still being drawn, and that the universe often speaks in whispers, not shouts. This first small mystery is merely the opening act, a prelude to gravitational puzzles of far greater magnitude that we encounter on a cosmic scale. But what happens when we zoom out from a single spacecraft to an entire galaxy? The rules of gravity, so reliable in our solar system, seem to break down completely. Picture a majestic spiral galaxy, a swirling disk of billions of stars. Just as planets closer to the sun orbit faster than those farther out, stars near a galaxy's bright center should whip around much faster than those on its dim, outer edges. This is what Newton's laws demand. Yet when astronomers like Vera Rubin measured these speeds, they found something astonishing. Stars on the galactic periphery, far from the central glow, were orbiting at nearly the same high velocity as the inner stars. The rotation curve was flat. It was as if every car on a vast circular highway, regardless of whether it was in the inner lane or the outer lane, was traveling at exactly 100 miles per hour. This should not be possible. At those tremendous speeds, the visible matter in the galaxy simply does not exert enough gravitational pull to hold onto these outer stars. They should be flung off into the void, yet they are not. Something invisible must be holding them in place. That something is a massive, unseen halo of dark matter, providing the extra gravitational glue to keep the galaxy intact. The evidence for this is overwhelming. We can calculate the mass of a galaxy from its light, but the gravitational pull we measure from stellar motions is far, far greater. The mass-to-light ratio is completely off. Without this dark matter scaffolding, galaxies would never have formed in the early universe, or they would have simply torn themselves apart long ago. This is not a minor issue. It implies that over 80% of all the matter in the universe is made of something we cannot see, touch, or directly detect. It is a ghostly presence that shapes the cosmos. Some scientists have proposed an alternative, a modification to Newton's laws of motion, known as MOND, which changes the rules of gravity on very large diffuse scales. But for most cosmologists, the gravitational evidence is so compelling that dark matter is now a cornerstone of our models. This leads to a profound and humbling question. Does the fact that we must invent an invisible substance to make our equations balance mean we are brilliant detectives? Or does it reveal a fundamental flaw in our understanding of gravity itself? The silent, spinning galaxies hold their secret for now. This same gravitational uncertainty extends from the silent depths of space to our very doorstep. When spacecraft like Galileo or Rosetta swung past Earth to steal a little orbital energy, using our planet's gravity as a cosmic slingshot, they exhibited a tiny, baffling quirk. Upon their closest approach, their velocity would change by a few millimeters per second, more or less than our most precise models predicted. This is the Flyby Anomaly. A shift so small it seems trivial, yet in the world of orbital mechanics, where trajectories are calculated with breathtaking accuracy, it is a glaring discrepancy. It is the equivalent of predicting a bullet's path to within a hair's width, only to watch it miss the mark by the width of a single sheet of paper. For scientists like John Anderson, who meticulously studied this effect, the challenge was immense. They investigated every conceivable cause, from the subtle drag of Earth's outer atmosphere to the mind-bending effects of general relativity known as frame dragging, where a rotating planet like Earth literally twists the fabric of space-time around it. They scrutinized our planet's slightly squashed shape, its oblateness, and the complex interplay of gravity in a rapidly spinning reference frame. Yet no single explanation could fully account for the data. The mystery deepened with each recorded flyby. The near-Shoemaker spacecraft's pass in 1998 showed a clear and undeniable speed boost that defied models. Other missions, like Rosetta, displayed the anomaly during some flybys but not others. The effect seemed to come and go without a clear, predictable pattern, making it not just a problem to solve, but a ghost to catch. How can our most trusted navigational techniques, the very same ones that have successfully guided probes to the moons of Jupiter and the rings of Saturn, still contain such a fundamental unknown? The Flyby Anomaly suggests that even here in our own celestial backyard, gravity may still have a few secrets left to tell. And if our understanding is incomplete so close to home, what other surprises await us in the vast, dark wilderness between the stars? Even our own galaxy's silent spin pales before a discovery that reshaped the entire cosmos. For decades, astronomers believed the universe's expansion was a cosmic echo, a gradual slowing down as the collective gravity of all matter pulled back on the great outward rush. Then, in the late 1990s, two teams of researchers led by Saul Perlmutter and Adam Rees pointed their telescopes at the most violent explosions in the universe, distant supernova. They used these brilliant flashes as cosmic mile markers, standard candles whose true brightness was known, allowing them to measure vast distances with precision. What they found was not a slowdown, but a shocking acceleration. The universe was not just expanding, it was flying apart at an ever-increasing rate, as if some mysterious, repulsive force was overpowering gravity itself. This discovery, which earned a Nobel Prize, forced a profound revision of our cosmic inventory. We now think that about 68% of everything in the universe is this mysterious repulsive energy, dark energy, a component that acts in direct opposition to the attractive force of gravity. The leading explanation is the cosmological constant, an intrinsic energy woven into the very fabric of empty space itself, causing a constant, gentle push outward. Another possibility is a dynamic field called quintessence, a kind of fifth force that could change over time. Measurements of the afterglow of the Big Bang, the cosmic microwave background, and the large-scale structure of galaxies all independently confirm this bizarre reality. The implications are staggering. If this acceleration continues unchecked, the ultimate fate of the cosmos may not be a slow fade, but a catastrophic big rip where the very fabric of space-time is torn apart, separating galaxies, stars, planets, and even atoms themselves. How do we reconcile a universe where the dominant force, the one dictating its final destiny, is not the gravity that holds us together, but a mysterious repulsion that pushes everything eternally apart? This very acceleration of the universe finds a strange, miniature echo in the architecture of our own solar system's frozen frontier. Far beyond the orbit of Neptune lies the Kuiper belt, a vast disk of icy debris left over from the solar system's formation. For a long time, astronomers expected this distant realm to be a placid, random collection of orbits, a gently stirred soup of small worlds like Pluto, all dutifully following the gravitational rules laid down by the known planets. But the outer solar system had a surprise in store. When researchers like Konstantin Batygin and Mike Brown mapped the paths of the most distant Kuiper belt objects, they found something deeply strange. Instead of a random scattering, the orbits of these extreme objects were mysteriously clustered together, as if an unseen hand had gathered them and aligned their long, elliptical paths in space. This peculiar orbital architecture is statistically like rolling a dozen dice and having them all land on the same number over and over again. The odds of this happening by pure chance are astronomically low. The most compelling explanation is the gravitational influence of a massive, unseen object, a hypothetical planet 9. Think of it as a cosmic shepherd, a super-Earth-sized world, perhaps 5 to 10 times the mass of our own planet, orbiting far out in the cold darkness. Over billions of years, its immense gravity could have sculpted the orbits of these smaller, detectable objects, herding them into the aligned patterns we observe today. This is a modern-day celestial detective story, where the primary clue is not a glint of light in a telescope, but a ghostly gravitational signature written into the paths of distant ice dwarfs like Sedna and 2012 VP-113. Their specific orbital details, their perihelion distances and arguments of perihelion, all point toward a single, massive source of perturbation. The search for this hidden world is now underway, using some of the most powerful telescopes on Earth to scan the vast swaths of sky where it might be lurking. The implications are staggering. Could our solar system, which we have mapped and studied for centuries, still harbor a major planet, a giant world whose presence we have only inferred from its subtle, gravitational whispers? This is not just a quest for a new world, it is a fundamental test of our gravitational models. Do we need to invent a new planet to explain the data, or is this a sign that our understanding of gravity itself needs revision in the cold, diffuse environment of the outer solar system? The Kuiper belt's clustered orbits stand as a silent, frozen question mark, a gravitational clue that our own cosmic neighborhood may be hiding its greatest secret just beyond the edge of our vision. Einstein's vision of spacetime was not a rigid stage, but a dynamic, malleable entity. A massive, rotating body like Earth does not simply sit within this fabric. it actively churns it, dragging the very coordinates of space and time around with its spin. This is the lens-thirring effect or frame dragging, a subtle but profound prediction of general relativity. Imagine a spoon spinning in a jar of thick honey, the sticky fluid twisting around it. In much the same way, our planet's rotation pulls the surrounding spacetime, causing the orbits of nearby satellites to slowly precess, to rotate in their orbital plane in a way that Newton's gravity simply cannot account for. Detecting this effect, however, was a monumental challenge. It required measuring a shift so tiny it is equivalent to watching the width of a human hair from over 6 miles away. To meet this challenge, scientists built one of the most precise instruments ever sent into space, Gravity Probe B. Led by physicist Francis Everett, this mission placed 4 ultra-precise gyroscopes in a perfect polar orbit around Earth. These were not ordinary gyroscopes. They were the most perfect spheres ever manufactured by humans, coated in niobium and chilled to near absolute zero. The idea was simple in principle, yet breathtakingly complex in execution. In a perfect, undisturbed spacetime, the spin axes of these gyroscopes would point in a fixed direction forever. But in the warped spacetime around our planet, 2 things would happen. First, the sheer mass of Earth would cause a large geodetic precession, a bending of the gyroscope's direction that was predicted and easily measured. Second, and far more elusive, was the frame-dragging precession caused by Earth's rotation itself. This effect was minuscule, a drift of just a few thousandths of a degree per year. For years, the Gravity Probe B team wrestled with unexpected sources of noise, tiny imperfections that threatened to drown out the signal they so desperately sought. Through painstaking analysis, they isolated the whisper of frame dragging, confirming Einstein's prediction with hard data. Complementary measurements from the LEGIO satellites, which tracked laser beams bounced off reflective orbiting spheres, further reinforced this finding. What does this mean for our understanding of gravity? It demonstrates with stunning clarity that gravity is not merely an attractive force between masses. It is the dynamic geometry of spacetime itself, a geometry that is not just curved by mass but actively stirred by motion. The very rotation of our planet imparts a real, physical twist to the universe around it. This confirmed that mass and motion are inextricably linked, capable of dragging the cosmos along for the ride. If our spinning world can so fundamentally influence the fabric of reality, what other gravitational dances are occurring around the universe's most extreme objects, where spacetime is not just stirred but whipped into a frenzy? Long before we puzzled over distant spacecraft, a tiny anomaly in our own solar system signaled a coming revolution. The planet Mercury, scorched and swift, follows an orbit that is not a perfect, repeating ellipse. Instead, its path slowly rotates around the Sun, tracing a delicate rosette pattern over centuries. Its point of closest approach, the perihelion, gradually advances. For generations, astronomers using Newton's laws could explain most of this drift by calculating the gravitational tugs from Venus, Earth, and the other planets. But a stubborn discrepancy remained. A tiny residual precession of about 43 arcseconds per century defied every Newtonian calculation. An arcsecond is an almost impossibly small unit, 1/3600th of a degree. This minuscule wobble was a ghost in the machine of the solar system, a flaw in the celestial clockwork that could not be ignored. The French mathematician Urbain Le Verrier, who had famously predicted the existence of Neptune from orbital irregularities, tackled this problem, convinced another unseen planet, which he named Vulcan, must be tugging on Mercury. But Vulcan was never found. The anomaly persisted for decades, a quiet but persistent crack in the foundation of classical physics. Then came Albert Einstein. As he wrestled with his theory of general relativity, he realized that the Sun's immense mass does not simply exert a force, it warps the very space-time around it. In this curved geometry, a planet's path is not a closed loop. The orbit itself must slowly process. Einstein performed the calculation for Mercury. The result was a precise, perfect match to the anomalous 43 arcseconds. He later wrote that this moment gave him heart palpitations as he saw that his theory resolved the puzzle with stunning elegance. This was not a new force or a hidden planet, but a fundamental rewriting of the rules. The successful explanation of Mercury's orbit became one of the 3 classic tests that cemented general relativity's place as our new theory of gravity. It moved us from a universe of invisible pulls to one of dynamic geometry, where mass tells spacetime how to curve, and curved spacetime tells mass how to move. The story of Mercury's wobble is a powerful lesson from history. It shows that the most profound breakthroughs can begin with the smallest, most stubborn inconsistencies. If a discrepancy of just 43 arcseconds per century could topple Newton's gravity and usher in Einstein's, what might the other gravitational anomalies we are discovering today ultimately reveal about the next great theory of everything? Our own galaxy is not drifting in stillness, but is caught in a vast, silent current. The Milky Way, along with the entire local group of galaxies, is rushing through the cosmos at over 2 million kilometers per hour toward a specific, mysterious point in the constellation Centaurus. This is the pull of the Great Attractor, a gravitational anomaly so immense it dictates the motion of thousands of galaxies across a region of space hundreds of millions of light-years wide. Its discovery in the 1970s and 80s came from mapping the redshifts of distant galaxies, which revealed a startling truth. While the universe expands overall, our entire galactic neighborhood displays a peculiar velocity, a clear deviation from the smooth Hubble flow, as if swept up in a colossal river. Astronomers like Alan Dressler led the charge, using these subtle deviations to trace the outlines of a hidden concentration of mass, a gravitational sink of unimaginable scale. The central challenge was our own galaxy's disk, the Milky Way's bright, dusty plain, a region astronomers call the zone of avoidance, completely blocks our optical view of this critical area of the sky. It was like trying to find the source of a mighty wind while standing in a blinding sandstorm. The breakthrough came with telescopes that could see in other wavelengths. Infrared observatories and powerful radio telescopes like Parkes in Australia finally pierced the cosmic dust, revealing a startling reality at the heart of the mystery. The Great Attractor is not a single monstrous object. It is a massive overdensity, the core of which is dominated by the Norma cluster, a rich gathering of galaxies, all embedded within an even vaster structure we now call the Laniakea supercluster. Laniakea, a Hawaiian word meaning immense heaven, is our true cosmic address. This colossal web of galaxies, containing the mass of roughly 100,000 Milky Ways, stretches over 500 million light-years. The Great Attractor is simply the deepest gravitational well within this supercluster, the central valley toward which all the galaxies, including our own, are slowly flowing. This phenomenon shows us that gravity's dominion extends to scales that defy human intuition. Entire clusters of galaxies behave like leaves caught in a whirlpool, their motions orchestrated not by what we can see, but by the hidden scaffolding of dark matter that defines the largest structures in the universe. What other immense, unseen basins of attraction are waiting to be discovered, their silent pulls guiding the cosmic dance on the grandest stage of all? Sometimes the most profound evidence is written not in starlight, but in the geometry of shadows. The bullet cluster offers exactly that, a cosmic crime scene where the visible evidence and the gravitational clues tell two starkly different stories. This is the aftermath of a violent collision between two galaxy clusters, a titanic event that has wrenched apart the components of the universe. As these immense structures slammed into one another at millions of miles per hour, their constituent parts behaved in ways that reveal their true nature. The individual galaxies, vast collections of stars separated by immense empty tracts, sailed right past each other like two swarms of bees passing through one another, largely unaffected. The hot gas filling the space between the galaxies, however, was a different story. This tenuous, multimillion-degree plasma, detected by its brilliant X-ray glow, could not avoid a collision. The gas particles slammed together, creating a spectacular shock wave, a cosmic bullet-shaped splash that gives the cluster its name. This gas, representing the bulk of the normal, visible matter, was slowed down and left lagging in the wake of the galaxies. But the real revelation came when astronomers mapped the cluster's total mass not by what glowed, but by how it bent the light from more distant galaxies behind it. This technique, called weak gravitational lensing, acts as a cosmic scale, measuring the heft of invisible matter by observing how its gravity warps the fabric of spacetime, distorting the images of background galaxies into faint, stretched arcs. The result was stunning. The peak of the mass, the true gravitational core of the system, was not located with the bright galaxies, nor was it with the lagging cloud of hot gas. Instead, the lensing map showed two distinct, massive blobs of invisible material, perfectly aligned with the two swarms of galaxies that had passed through unharmed. This is the ghostly signature of dark matter. The interpretation is as elegant as it is profound. The dark matter, whatever it is, must be collisionless. It does not interact with itself or with normal matter in any significant way except through gravity. Just like the galaxies, the dark matter halos pass through the collision completely unscathed, carrying the majority of the cluster's mass with them. This observation, led by teams using the Chandra X-ray Observatory and the Hubble Space Telescope, presents a monumental challenge for theories that try to explain galactic rotations by modifying gravity alone, such as MEN. Those theories would predict that the gravitational lensing, the warping of light, should follow the distribution of the visible matter, the stars, and the gas. But it does not. The gravity is clearly anchored to something unseen, something that marched straight through the cosmic collision. The bullet cluster gives dark matter a face, or at least a gravitational shadow. It shows us that this mysterious substance is not just a mathematical contrivance to balance an equation. It is a physical entity that can be mapped, that has location and mass, and that behaves in specific, predictable ways under the most extreme conditions. If we can watch dark matter being separated from normal matter in a cosmic accident, what other secrets about this invisible cosmos are waiting to be revealed in the aftermath of other violent celestial events? Yet the immense structures shaped by dark matter are governed by a force that seems to defy its own nature on the grandest scale. The vacuum of space is not truly empty. According to quantum field theory, every tiny patch of nothingness is a seething foam of virtual particles, constantly flickering in and out of existence. This quantum frenzy should imbue empty space with a staggering energy density, a phenomenon known as zero-point energy. This energy would act as a cosmological constant, a term Einstein once introduced and later discarded. If our best theories are correct, this vacuum energy should be so colossal that its repulsive gravity would have torn the infant universe apart before the first stars could ever form. The predicted value is astronomically large, yet when we observe the actual acceleration of the cosmos, the measured value of dark energy is incredibly small and positive. The theoretical prediction and the observational reality are not just slightly different, they are wrong by a factor of 1 followed by 120 zeros. This is the cosmological constant problem, the single most embarrassing discrepancy in all of science. It is a number so vast it transcends mere error and points to a fundamental crisis in physics. Our two most powerful theories, general relativity for the cosmic scale and quantum mechanics for the microscopic realm, give utterly incompatible answers for the simplest question imaginable: what is the energy of nothing? Nobel laureate Steven Weinberg wrestled with this profound mismatch, arguing it reveals a deep flaw in our understanding of how gravity couples to the quantum world. One proposed solution is the anthropic principle, a controversial idea suggesting our universe is just one among a vast multiverse. In most universes, the cosmological constant is too large for galaxies or life to form. We simply find ourselves in one of the rare, finely tuned pockets where the value is small enough to allow our existence. Other physicists seek more concrete answers in theories like supersymmetry, which posits a hidden partner for every known particle. This symmetry could, in principle, cancel out the vacuum energy to near zero, but no evidence for these partner particles has been found. Data from the Planck satellite precisely measures the dark energy density, confirming its tiny value and deepening the mystery. The problem forces us to confront a philosophical quandary. Is the universe we observe an inevitable consequence of physical laws, or is it a strange and improbable accident? This is not a minor accounting error. It is a glaring sign that our current map of reality is profoundly incomplete, that something essential is missing from our picture of how the cosmos truly works. How can the energy of the void, of absolute nothingness, present such an immense and enduring challenge to everything we think we know? Even the most perfect snapshot of the universe's infancy seems to hold a strange, unintended reflection of ourselves. The cosmic microwave background, the ancient afterglow of the Big Bang, is the farthest back in time we can possibly see. This faint, cold light bathing the cosmos is expected to be the very definition of randomness, a featureless sea of tiny temperature fluctuations with no preferred direction, confirming the universe is fundamentally the same everywhere. Yet the most detailed maps from the WMAP and Planck satellites reveal a ghostly pattern that should not exist. On the very largest scales, the fluctuations in this primordial light are not random. They appear to align ever so slightly along a specific axis that seems to point back toward our own solar system. This eerie correlation, whimsically nicknamed the axis of evil, directly confronts one of cosmology's most sacred principles, the assumption that the universe has no center and no special direction. The problem lies in the details of the CMB power spectrum, the mathematical way we describe the size and distribution of these hot and cold spots. The low-order multipoles, specifically the quadrupole and octupole moments which represent the very largest ripples in the early universe, are not oriented randomly as they should be. Instead, their planes are mysteriously aligned with each other, and their geometry seems to correlate with the plane of our solar system and the direction our sun is moving through space. The odds of this happening by pure chance are extremely low. For physicists like Kate Land and Joe Megiddo, this presents a profound dilemma. Is this alignment just a bizarre statistical fluke, a one-in-a-million coincidence in our particular cosmic neighborhood? Could it be an unknown systematic error, some subtle contamination from our local environment or the instruments themselves that we have not yet accounted for? Or is it a genuine crack in the cosmological principle, a hint that the universe on its grandest scales is not isotropic, but has a fundamental anisotropy, a preferred direction woven into its fabric? This axis is also curiously aligned with other large-scale anomalies, like the mysterious and vast cold spot in the CMB, a region of space far colder than our models can easily explain. The implications are staggering. If the axis of evil is real, it suggests that our location in the cosmos is not entirely random, that the largest structures in the universe are somehow connected to our local frame of reference. It raises the unnerving possibility of a cosmic conspiracy, where the universe's earliest light carries a faint imprint of the solar system that would not exist for billions of years. Could the vacuum of space have a structure that picks out a special direction, much like a crystal has a grain? The debate over the axis of evil's significance keeps cosmologists awake at night, forcing them to question whether our most fundamental snapshot of reality is truly a portrait of the cosmos, or if we are unknowingly seeing a reflection of our own place within it. The faint glow of the cosmic microwave background does more than just illuminate the infant universe. It acts as a cosmic roadblock for the most energetic particles ever seen. These are ultra-high-energy cosmic rays, single protons or atomic nuclei carrying as much kinetic energy as a professionally pitched baseball, all compressed into a subatomic speck. According to a prediction made by physicists Greisen, Zatsepin, and Kuzmin, such a particle screaming across intergalactic space should not be able to travel very far. It is destined to collide with the relic photons of the CMB, a sea of light that has cooled to just a few degrees above absolute zero. For a normal particle, this bath of cold light is insignificant. But for a proton with energy 100 million times greater than what the Large Hadron Collider can produce, each CMB photon is boosted into a formidable obstacle. The collision creates a new particle, a pion, sapping the cosmic ray's energy in a process that theoretically imposes a strict upper limit on the energy we should ever detect from distant sources. This is the GZK cutoff, a fundamental energy ceiling for the universe's travelers. Yet the universe, it seems, has a habit of breaking its own rules. Massive observatories like the Pierre Auger Array, sprawling across dozens of square kilometers, have repeatedly recorded the telltale showers produced by cosmic rays that smash through this predicted ceiling. These are super GZK events, particles arriving with energies that, according to our best models, should have been drained away over a long journey. The immediate, tantalizing explanation is that they come from relatively nearby sources, from our own cosmic backyard within 100 million light-years or so. Perhaps they are blasted from the cores of active galactic nuclei, where supermassive black holes act as natural particle accelerators of unimaginable power. But here, another mystery deepens. When we try to trace these ultra-high-energy particles back to their origin, their paths are scrambled. The weak but pervasive magnetic fields that thread the space between galaxies bend the trajectories of these charged particles, making it nearly impossible to point back to a single, brilliant source in the sky. The sources remain hidden, ghostly accelerators in the void. The continued arrival of these rule-breaking particles forces a more radical question. What if the GZK process itself is not working as we think? The calculations behind the cutoff rely on the unshakable principles of Einstein's special relativity, specifically Lorentz invariance, which states that the laws of physics are the same for all observers regardless of their speed. But some theories of quantum gravity, attempts to unify the very large with the very small, suggest that spacetime might not be perfectly smooth. At the near impossibly tiny Planck scale, it could have a foamy, granular texture. This minuscule graininess could introduce tiny violations of Lorentz invariance, subtly altering how particles interact at these extreme energies. Perhaps a super-energetic proton experiences spacetime differently, allowing it to bypass the GZK process entirely and travel much farther than we thought possible. The fact that we see these particles at all could be the first, faint hint that we are witnessing the breakdown of relativity itself at energies we can never hope to recreate on Earth. These cosmic rays are more than just random high-speed debris. They are messengers from the most extreme regimes of nature, carrying encoded clues about the fundamental symmetry of the cosmos. Each one that strikes our atmosphere is a direct challenge, a single data point that places our understanding of gravity and the quantum world on a dramatic collision course. Even our most fundamental constant, the rate of the universe's expansion, is now a subject of fierce debate. This is the Hubble Tension, a stubborn disagreement between two of the most trusted methods for measuring the Hubble constant. On one side, we have the local distance ladder, a meticulous cosmic measuring tape built step by step. Astronomers begin with geometric parallax to nearby stars, then use pulsating stars called Cepheid variables as standard candles to gauge distances to galaxies hosting Type Ia supernova. These supernova, with their remarkably consistent peak brightness, then allow us to measure the expansion rate across vast cosmic distances. Teams led by Adam Rees, using the SH0ES project data, arrive at a value around 73 kilometers per second per megaparsec. This means that for every megaparsec of distance, about 3.26 million light-years, a galaxy appears to be moving away from us 73 kilometers per second faster. This is our universe's current expansion speed as measured by its modern inhabitants. Yet, when we look back to the universe's infancy, we get a different answer. The Planck satellite mapped the cosmic microwave background in exquisite detail, capturing the faint imprint of the first light. By analyzing the subtle patterns in this afterglow, scientists can deduce the universe's composition and, using the standard lambda CDM model, extrapolate forward to predict what the Hubble constant should be today. The Planck result is unequivocal, around 67. This is not a minor difference. With uncertainties shrunk to just over 1% for each method, the discrepancy now stands at a confidence level of 4 to 5 sigma, meaning the chance it is a mere statistical fluke is less than 1 in a million. Both methods are exquisitely refined, yet they stubbornly refuse to agree. This is not just a numbers game, it is a direct challenge to our standard model of cosmology. Could there be an unknown systematic error, some subtle miscalibration in how we measure Cepheid distances or interpret the CMB data? Astronomers like Wendy Friedman have pursued alternative cosmic ladders using different stars like the Red Giant Branch to cross-check the results, yet the tension persists. The more likely and more thrilling possibility is that our model is incomplete. Perhaps dark energy is not a constant but is evolving, growing stronger over time. Maybe an early form of dark energy gave the young universe an extra push. Other proposals include exotic neutrino interactions or even a modification to gravity itself on the largest scales. The Hubble tension is more than a puzzle for cosmologists. It is a potential crack in the foundation of our cosmic understanding. If the universe is truly expanding faster than our best models predict, what new, undiscovered physics is required to explain the journey from its first whisper to its present-day rush? Even our most pristine map of the cosmos is not without its blemishes. Gaze upon the full sky image of the cosmic microwave background, and your eye might be drawn to a particular region in the constellation Eridanus. This is the CMB Cold Spot, an anomalous patch of sky that is significantly colder and vaster than our standard models can easily explain. It is not just a tiny fluctuation. This spot is about 0.00015 Kelvin colder than its surroundings and spans a region tens of degrees across, so large it could cover 1,000 full moons. In a universe governed by simple inflationary physics, such a feature should be astronomically rare. The statistical probability of a spot this cold and large appearing in a purely random Gaussian field is less than 2%. Its very existence challenges the standard narrative of a smooth, featureless early universe. So what could create such a profound cosmic chill? One leading explanation involves a supervoid, an immense and largely empty region of space lying between us and the CMB. As light from the primordial glow travels through such a void, it must climb out of a gravitational well. According to general relativity, photons lose energy during this climb, a phenomenon known as the integrated Sachs-Wolf effect, creating a cold spot in the CMB temperature map. Yet, when astronomers searched for this proposed supervoid in galaxy surveys, the results were mixed. No corresponding void of sufficient scale has been definitively confirmed, leaving the mystery wide open. This has led physicists to consider far more exotic origins. The cold spot could be a cosmic texture, a topological defect in the very fabric of space-time, a kind of knot that formed during a phase transition in the universe's first fleeting moments. As this texture evolved, it would have imprinted a unique temperature signature on the CMB, a cold spot exactly like the one we see. An even more mind-bending proposal comes from theorists like Laura Mersini-Horton, who suggests this anomaly could be evidence of a collision with another universe in the vast multiverse landscape. In this scenario, the cold spot is a bruise on our cosmos, a remnant of a primordial impact with a sibling bubble universe. Each of these explanations, from the supervoid to the cosmic texture to the multiverse collision, points toward physics beyond our simplest models. The cold spot is a stubborn enigma, a reminder that our clearest window into the early universe might still be showing us reflections of phenomena we are only beginning to comprehend. Could this single, cold fingerprint on the sky be the first tangible evidence of a reality far grander and more complex than we ever imagined? Even the first few minutes of the universe hold a lingering chemical mystery. In the blistering heat of the Big Bang's first 3 minutes, a process known as Big Bang nucleosynthesis forged the universe's first atomic nuclei. Protons and neutrons collided and fused, creating the primordial ingredients for everything to come. The calculations for this cosmic recipe are stunningly precise. The predicted amounts of deuterium and helium-4 align almost perfectly with what we observe in the oldest clouds of gas. But for one element, the math goes completely wrong. The models predict that the universe should contain about 3 times more lithium-7 than we can actually find in the ancient stars of our galactic halo. This is the cosmological lithium problem, a small but profound mismatch from the very dawn of time. Imagine a master chef following a perfect recipe, only to find one key ingredient is consistently and mysteriously missing from the final dish. Nuclear astrophysicists like Brian Fields have scrutinized every step of the process. They have checked and rechecked the nuclear reaction rates, the precise chains of fusion that built these light elements. They have incorporated the exquisitely measured baryon density from the cosmic microwave background, which tells us exactly how much normal matter was available to cook with. Yet the answer remains stubbornly the same. The universe should have 1 lithium-7 atom for every 2 billion hydrogen atoms, but the oldest stars show only about 1 for every 10 billion. Where did all the lithium go? One possibility is that our understanding of the stars themselves is flawed. Perhaps these ancient, metal-poor stars have internal processes that slowly drag surface lithium down into their hotter cores, destroying it and making them appear deficient. But many astronomers argue this cannot account for the full discrepancy. This leads to a more thrilling possibility that new physics was at play in that primordial inferno. Exotic, undiscovered particles may have been present. Theorists have proposed that certain supersymmetric particles, like neutralinos, could have decayed in the early universe, injecting just enough energy to disrupt the delicate nuclear balance and destroy the fragile lithium nuclei. The lithium problem is a tiny crack, but it runs deep into the foundation of our knowledge. It connects the vast scale of cosmology to the quantum world of particle physics. Why would the universe, in its first moments, get the recipe for something as simple as lithium so wrong? This elemental discrepancy is a quiet but persistent whisper from the dawn of time, suggesting that our standard model of particle physics is still missing a few ingredients. The vast cosmic voids between galactic filaments are not merely empty space, they are active participants in the cosmic drama. One of the most intriguing is the Eridanus Supervoid, a staggering bubble of nothingness that may hold the key to the mysterious CMB Cold Spot. This proposed region of profound emptiness spans an almost unimaginable billion light-years, a volume so large it could contain tens of thousands of galaxies, yet it appears to hold far fewer than it should. When the ancient light of the cosmic microwave background passes through such a void, something strange happens. The photons are climbing out of a gravitational well, but because our universe is dominated by dark energy and its expansion is accelerating, that well is actually becoming shallower over time. This is the integrated Sachs-Wolf effect in action. As a CMB photon enters the void, it falls into a potential well, gaining a minuscule amount of energy. But as it travels through, the expansion of the universe causes the well to decay, so when the photon climbs out, it loses more energy than it gained. The net result is a cold spot, a slight reddening and cooling of the primordial light, imprinted directly onto our maps of the sky. The existence of such a void was championed by astronomers like István Sapudi, who painstakingly combined data from galaxy surveys like WISE and 2-micron all-sky survey to map the large-scale structure in the direction of the cold spot. Their work revealed a significant underdensity, a genuine supervoid, but here the mystery deepens. For this void to single-handedly create the profound chill of the cold spot, it would need to be both emptier and larger than our standard cosmological model, lambda CDM, readily allows. The statistics of the early universe, as seen in the CMB, suggest that matter fluctuations should be Gaussian, meaning a void of this extreme scale and depth is statistically very rare, perhaps improbably so. This places cosmologists in a difficult position. Is the Eridanus Supervoid a rare but natural cosmic occurrence, a statistical outlier that just happens to align with the cold spot by sheer chance? Or is its very existence a challenge to our models, a sign that the universe creates larger and emptier voids than we thought possible? The alternative is that the void and the cold spot are not causally connected at all, but are simply aligned along our line of sight, a cosmic illusion that tricks us into seeing a relationship where none exists. This single patch of sky weaves together three great cosmic mysteries: the distribution of galaxies, the nature of dark energy, and the primordial afterglow of creation. It shows us that the universe's largest structures, even its grandest absences, can reach across billions of years to leave a ghostly fingerprint on its very first light. Are we witnessing the subtle, long-range influence of nothingness itself, or is this a simple coincidence written on a cosmic scale? The answer will tell us not just about one cold spot, but about the fundamental architecture of everything. Our own star holds a secret from its youth that challenges our grasp of stellar physics. Standard models of how stars evolved tell us that billions of years ago, the Sun was significantly dimmer, shining with only about 70% of its current brilliance. For a young Earth orbiting at its present distance, this should have meant a global, deep freeze, a world encased in ice from pole to pole. Yet the geological record tells a completely different story. Ancient rocks from the Archean Eon, over 2 billion years old, bear the unmistakable chemical fingerprints of liquid water, and we find evidence of life itself thriving in those primordial seas. This is the faint young sun paradox, a stark contradiction between the predicted climate of early Earth and the environment that actually existed. How could a planet wrapped in a faint sun's weak embrace have been so warm? The paradox was first seriously tackled by scientists like Carl Sagan and George Mullen, who realized the implications were profound. The immediate answer seems to lie not with the star, but with the planet's atmosphere. A much thicker blanket of greenhouse gases, perhaps dominated by carbon dioxide and methane, could have trapped enough heat to offset the solar deficit, creating a natural planetary thermostat. But this climatic solution only deepens the astrophysical mystery. Our entire understanding of the sun's life cycle is built upon the standard solar model, a precise calculation of how gravity compresses the core, driving nuclear fusion and governing the star's steady brightening over billions of years. This model is a delicate balance of forces incorporating gravitational settling, nuclear reaction rates, and the complex transport of energy from the core to the surface. If the early Earth required a different kind of sun, one that was somehow warmer than our models predict, then perhaps our understanding of that gravitational engine is incomplete. Could the early solar constant have been different due to some exotic particle physics or a higher rate of solar activity? The resolution of this paradox forces an intimate connection between the science of the very large and the very small. The history of our planet's climate becomes a direct test of our theories about stellar interiors. Are we correctly modeling the gravitational equilibrium and nuclear fusion at the heart of our sun, the very processes that dictate the lifespan of stars and the potential for life across the cosmos? The faint young sun reminds us that a planet's climate is not just a local story, but a chapter written by the distant, ferocious physics of its star. Far beyond the last known planets in the sun's gravitational grip lies a ghost. This is the Oort Cloud, a vast, hypothetical shell of frozen relics left over from the solar system's violent birth. No telescope has ever seen an object there, for they are too dark and too far, yet we know it must exist because of the long-period comets that occasionally plunge into our skies from every conceivable direction. These icy messengers do not arrive from the flat plane of the planets, but from a spherical halo surrounding us, a fossilized bubble of our own creation. The very concept proposed by the Dutch astronomer Jan Oort relies on a delicate celestial balance. The sun's gravity is just strong enough at that immense distance to hold onto these ancient ice balls, but weak enough that the gentlest of nudges can send one tumbling inward on a million-year journey. That nudge can come from a passing star whose gravity can stir the cloud like a hand moving through mist. It can come from the tidal pull of the entire Milky Way galaxy, a subtle but constant torque. It can even come from the hypothetical planet 9, whose proposed orbit would act as a slow, gravitational metronome, ticking over eons. Dynamicists like Julio Fernandez have spent careers modeling this complex dance, showing how the galaxy itself sculpts the cloud's outer fringes. Yet the very stability of this distant reservoir is a profound puzzle. Over the 4.5 billion-year age of our solar system, our sun has drifted through different galactic neighborhoods, experiencing countless stellar flybys. We know one happened recently, just 70,000 years ago, when a small binary system known as Skolz's star passed through the outer Oort Cloud. Such encounters should have stripped away a significant portion of the cloud's population, yet we still see a steady trickle of comets. This suggests the Oort Cloud must be far more massive than we think, perhaps containing several Earth masses of material to have survived this long. Its structure is thought to have two parts, a vast spherical outer cloud and a denser, more massive inner core known as the Hills cloud, which could be the true source of many comets. This inner region might be the very one feeling the gravitational influence of a hidden planet 9, its alignment potentially explaining why some comets are kicked inward. But modeling this is a Herculean task, requiring simulations that account for the Sun's motion around the galaxy, the gravity of other stars, and the initial chaos of planetary migration. The Oort Cloud is not a static museum piece. It is a dynamically active frontier, constantly being reshaped by forces both internal and galactic. Does its continued existence and the pattern of comets we observe mean our models of its formation and survival are correct? Or is it a sign that we are still missing a major piece of the gravitational puzzle in our own cosmic backyard? This most distant region of our solar system, inferred only from ghostly trajectories, stands as a testament to gravity's long reach and its enduring mysteries. The frozen fringes of our solar system are a celestial archive, preserving records of a violent and chaotic past. Far beyond the graceful orbits of the giant planets lies a realm of small, icy bodies known as Trans-Neptunian objects. These are not the placid, predictable worlds you might expect at the edge of a stable system. Many, especially a class called sedenoids and extreme TNOs, follow bizarre, stretched-out paths. Their orbits are so elongated that they spend most of their lives in a deep, cold darkness, far from any planetary influence, yet they never swing close enough to Neptune to feel its direct gravitational pull. This isolation makes their next behavior utterly baffling. Despite their vast distances, the orbits of these objects are mysteriously clustered. Their points of closest approach to the Sun, their perihelia, are grouped together in space, and the angles describing the orientation of their orbits, the argument of perihelion and longitude of the ascending node, are strangely aligned. This is not a random scattering. It is a synchronized dance, and the odds of it happening by pure chance are astronomically low. Researchers Konstantin Batygin and Mike Brown have demonstrated through extensive computer simulations that a single, unseen architect could be responsible. A distant planet with a mass between 5 and 10 times that of Earth, moving on a long, eccentric orbit of its own, could act as a gravitational shepherd. Over billions of years, its persistent tug would have herded these icy dwarfs, locking their orbits into a stable, aligned configuration through a process known as secular perturbations. This is a slow, graceful orbital waltz where the gravity of the distant perturber gradually twists and aligns the paths of the smaller bodies, without the need for close encounters. Objects like Sedna and 2012 VP-113 are key witnesses. Sedna, for instance, takes over 11,000 years to complete one orbit and never comes closer than about 76 times the Earth-Sun distance. Its path and the paths of its kin are the primary clues pointing toward this hidden world. The hunt for Planet 9 is now a monumental effort, using telescopes like Subaru to scan the vast, dark sky where it is predicted to be. The challenge is immense, as the planet would be incredibly faint and moving slowly against the background stars. This gravitational signature hidden in the dynamics of icy worlds is a modern-day celestial mechanics puzzle, a direct echo of the 19th century discovery of Neptune from the wobbles of Uranus. But this time, the scale is far grander and the potential discovery even more profound. What other secrets about the solar system's violent youth and its true extent are written in the cryptic, looping paths of these distant ice dwarfs? Their orbits are a message from the outer darkness, a cosmic cipher that, once decoded, could reveal a new member of our own solar family. Our galaxy's graceful spiral is not just a structure, but a living history book, and the Gaia satellite is giving us the ability to read its pages. By charting the precise motions of over 1 billion stars, this space observatory has uncovered a dramatic chapter written in starlight, a population of stars moving in starkly different paths. Instead of the more circular orbits typical of the galactic disk, these stars plunge in and out of the galactic center on highly radial, elongated trajectories, a pattern so distinct it earned the whimsical nickname the Gaia sausage. This is no random collection. It is the ghost of an ancient cataclysm, the remnant of a dwarf galaxy that collided with and was consumed by the young Milky Way roughly 8 to 10 billion years ago. Teams of astronomers like those led by Vasily Bolokurov and Amina Helmi used Gaia's exquisite proper motion data to trace these stellar paths backward in time, revealing their common, violent origin. The progenitor galaxy, now named Gaia Enceladus, was substantial with a mass of about 1 billion suns. When it merged with our own, the gravitational chaos was immense. The orderly orbits of stars in both galaxies were violently disrupted, flung onto new, plunging routes that we can still detect today. The evidence is not just in their motion. The chemical fingerprints of these sausage stars are different, containing a lower proportion of heavier elements or metals compared to native Milky Way stars of a similar age. This confirms they were forged in a separate, smaller galaxy with a slower pace of star formation and chemical enrichment. This single, ancient merger did more than just add stars. It is believed to have contributed significantly to the Milky Way's halo of ancient stars and may have even puffed up its thick disk, fundamentally shaping the galaxy we call home today. The Gaia sausage forces us to abandon simple pictures of galaxies forming in isolation. It shows that galaxy growth is hierarchical, built through a series of violent gravitational encounters and cannibalism. Our galaxy's gravity is not a static force but a dynamic archive, preserving the memory of this colossal impact in the looping paths of countless stars. What other galactic fossils are hidden in the stellar halo, their stories waiting to be decoded by the next generation of precise astrometry? This single structure proves that our Milky Way's past was far more turbulent and dramatic than we ever imagined. Deep in the heart of our galaxy, a cosmic drama unfolded in real time. The supermassive black hole known as Sagittarius A* holds court at the galactic center, a gravitational titan with the mass of 4 million suns. In its presence, a peculiar object called G2 was spotted on a death-defying trajectory. This dusty, enigmatic cloud was on a highly eccentric orbit, a 300-year path that would bring it perilously close to the black hole's event horizon. Astronomers around the world trained their most powerful telescopes on the scene, anticipating a spectacular show. The laws of physics seemed to dictate a grim fate. As G2 approached its closest point in 2014, the black hole's immense tidal forces should have stretched and shredded it into a stream of gas. This stellar snack was expected to create a brilliant flare as the material spiraled into the abyss, a flash that would illuminate the dynamics of accretion. But the universe had a surprise in store. G2 did not tear apart, it survived. The object was stretched, yes, its structure distorted by the overwhelming gravity, but it emerged from its closest approach fundamentally intact. This was not the behavior of a simple, diffuse cloud of gas. Its survival pointed to something with a stronger will to live, an object with its own significant gravity holding it together against the black hole's pull. The leading theory suggests G2 is not a cloud at all, but a star cloaked in a thick, extended envelope of gas and dust. Another possibility is that it is the product of a stellar merger, a single object born from the violent collision of two stars, giving it the mass and cohesion to withstand the encounter. Experts like Andrea Ghez and her team used the Keck Observatory to track G2's every move, watching its brightness and structure change. They were not just watching an object, they were conducting a unique experiment in one of the most extreme gravitational environments in the galaxy. The key to its survival lies in a concept called the Roche limit. This is the point where an object's self-gravity, its own internal pull holding it together, is overwhelmed by the tidal gravity of a massive body it is orbiting. For a wispy gas cloud with no self-gravity, the Roche limit is vast, and it would be torn apart long before reaching its closest approach. But for a dense, massive star, the Roche limit is much smaller, lying incredibly close to the black hole itself. G2 passed about 200 astronomical units from Sagittarius, a star, well outside the Roche limit for a star, but deep inside the zone where a simple cloud would be destroyed. Its ability to hold together revealed its true, massive nature. This event did more than just identify one strange object. It opened a window into a hidden population. The galactic center is likely teeming with such dust-enshrouded stars or stellar remnants, objects that are normally invisible to our telescopes. G2's journey showed that the environment around a supermassive black hole is not a simple vacuum where matter falls in freely. It is a complex, dynamic arena where dense, massive objects can navigate the edge of oblivion. What other gravitational survivors are orbiting in the dark, their presence only hinted at when their paths brush against the ultimate boundary. The story of G2 is a testament to the raw power of gravity and the enduring mystery of what can endure at its very limit. Gravity's grand cosmic blueprint appears to have a flaw in its smallest details. Our most sophisticated computer simulations of the universe, based on the prevailing lambda-CDM model, paint a very specific picture of how structure forms. In this narrative, the cosmos builds itself from the bottom up, with tiny clumps of dark matter emerging first from the primordial soup. These small halos then merge like droplets of water to form the vast galaxies we see today. The simulations, which track only the gravity of dark matter, predict a universe teeming with these small, foundational halos. Thousands of them should be orbiting a galaxy like our own Milky Way, each a gravitational potential well deep enough to host a small, visible satellite galaxy. Yet when we look up at the sky, we find only a few dozen. This is the missing satellites problem, a glaring mismatch between the dark matter cosmos we simulate and the luminous universe we actually observe. It is as if we predicted a vast, bustling metropolis, but upon arriving, we found only a handful of buildings scattered in a field. The discrepancy was truly unmasked as supercomputers grew more powerful, with cosmologists like Giulio Navarro, famous for describing the universal density profile of dark matter halos, watching in fascination as their virtual universes populated with a vast, unseen infrastructure of subhalos. The question became urgent. Where are all the galaxies that should be lighting up these countless gravitational anchors? The leading explanation points not to a failure of dark matter, but to the complex and often violent physics of ordinary matter. In the earliest epochs of the universe, the cosmos was flooded with intense ultraviolet radiation from the first stars and quasars, a period known as reionization. This cosmic background radiation could have heated the sparse gas within the smallest dark matter halos, preventing it from cooling, condensing, and collapsing to form stars. Imagine trying to light a candle in a strong wind. The fuel is there, but the environment snuffs out the flame before it can catch. Furthermore, in those halos that did manage to form a first generation of stars, the resulting supernova explosions could have been cataclysmic. These stellar detonations would have unleashed powerful winds, blowing the remaining star-forming gas completely out of the feeble gravitational grip of the small halo. effectively sterilizing it and shutting down future galaxy formation. This process, called baryonic feedback, suggests that the vast majority of those predicted dark matter subhalos are not missing at all. They are simply dark, failed galaxies, orbiting our own in profound silence, their potential for light long since extinguished by astrophysical violence. Observational evidence from surveys like the Sloan Digital Sky Survey and the Dark Energy Survey has begun to find the faintest, most diffuse dwarfs, a population of ultra-faint galaxies that were previously invisible. Each new discovery helps to bridge the gap, but the count is still far short of the simulated multitudes. This has led some physicists to propose a more fundamental revision. What if dark matter is not completely cold, but slightly warm? Warm dark matter would consist of particles moving at a fraction of the speed of light, possessing just enough kinetic energy to smooth out the very smallest scales of structure. This would naturally suppress the formation of the tiniest halos, bringing the predicted numbers more in line with what we see. The missing satellites problem forces us to confront the intricate dance between the dark and the light. It shows us that gravity alone is not enough to build a visible universe. The presence of a deep gravitational well is merely an invitation, one that can be rescinded by the searing radiation of the first dawn or the explosive death of a star. Are we looking at a universe where most gravitational islands remain forever shrouded in darkness, or does their absence point to a deeper truth about the fundamental nature of the matter that shapes our cosmos?